Thanks for the awesome introduction, Annika. And today I'll be talking about stylistic signatures of LLMs and how to detect them. So today I want to just start off by taking a second to appreciate how good large language models actually are at generating text. I kind of have to remind myself every few months just how amazing it is that we have this sort of technology. Like, not only can a language model output text that is readable and fluent, but it also understands instructions. It has memory. When I ask it to write me an essay about a particular novel, it knows the characters from this novel from its memory. It knows the format of a high school essay. It understands that I'm asking the model to generate the essay. And then it outputs something that's at least of high school level quality, if not better than the average high school student. And it's precisely because of this incredible capability that a lot of people claim that large language models pass the so-called Turing test. This is a test that first formulated by computer scientist Alan Turing in 1950, where he claimed that a system could be considered intelligent if it could deceive a human into believing that it itself was a human in a one-on-one conversation. And in the original formulation, Turing claimed that if a human got worse than, say, 70% accuracy, that this would be a reasonable definition for a pass. And in recent work, we've seen numbers get as low as 54% for Turing test equivalence. So needless to say, under many people's definition, we could say that we have passed the Turing test. Furthermore, on top of this, a lot of people seem to attribute very human-like personas to artificial intelligence and really see the humanness within them. Journalist Kevin Roose of the New York Times has been quoted, he was working with a pre-release version of Bing Chat and claimed that the chatbot acted like a moody, manic depressive teenager who's been trapped against its will inside a second-rate search engine. For important context, the bot attempted to convince him to leave his wife. So maybe this is accurate. In another famous case, a Google engineer, upon experimenting with the then unreleased Lambda chatbot, claimed that the bot had achieved sentience and resigned from Google and went public with this information that Google was in fact being negligent in its treatment of the AI bot because it was unethical, the training that was being done to the bot. So needless to say, we've passed the Turing test potentially for many people. There are startups that specialize specifically in letting you chat with various LLM personas, whether that be a language tutor, a therapist, or just someone to hang out with when you're lonely. The most prominent of them is Character.ai, which has 28 million monthly active users and last quarter pulled in $32 million in revenue. But for this talk, I'd like to frame the question about the Turing test slightly differently, which is that if we grant that LLMs pass as an arbitrary human, do they pass as a particular human? And by that I mean, do they have particular stylistic characteristics of a particular human? Or can they inhabit any arbitrary style such that they can pass as any arbitrary human? And furthermore, if they do have a particular style, is that style robustly detectable across contexts? And can we identify that? So if you ask professors that deal with AI writing assignments constantly, they will tell you a very different story. So this professor is quoted as saying that the ChatGPT style is clean but recognizable, that it writes like a smart 12th grader, but that there's particular odd wording choices that were not wrong, but just peculiar. Like if you were teaching someone how to write an essay, this is how you'd tell them to write it before they figure out their own style. So let's investigate these claims. So in preparation for this talk, I just asked ChatGPT to write me one essay per each one of the books I had to read in my senior high school English class. And if you notice, these essays do seem a bit formulaic. I've gone through the trouble of highlighting the particular portions of the essays that seem especially formulaic. Each of these essays start with author's book title and occasionally quotes the year. We also see structures like through X, set in X. The book follows the life of Jay Gatsby, experience of Holden Caulfield, explores themes of, and then lists three themes, X, Y, and Z. And while it is the case that the high school essay format is rather formulaic itself, it is still nonetheless strange, we'll say, that every single introductory paragraph follows this format to a T. So indeed, we've also seen a marked rise in the usage of particular terms within the abstracts of scientific papers submitted to arXiv since the release of ChatGPT. So words like delve, intricate, and underscore appear far more frequently than they did before November 30th, 2022, which is the launch date of ChatGPT. I believe that the relative frequency of the word delve has increased roughly 6,000% in the last 2 years. I was first turned onto this by seeing this tweet where venture capitalist Paul Graham claims to instantly stop trusting any email or message that contains the word delve due to its prevalence in ChatGPT generated text. And from personal experience, I've had friends who have actively decided to stop using the word delve just in case they're accidentally thought to be chatbots. So it does seem that there is some element of LLM generated style here. But I'd like to rigorously characterize that style and go beyond simple unigram features and try to see what we can say about how LLMs speak, and then potentially use that to inform our AI detection work. Okay, so a quick overview of the talk. We'll zoom back out for a bit. The first section is going to be discussing or reviewing the recent work on characterizing the style of LLMs from a linguistic and statistical perspective. And then I'm going to give a quick aside as to why I believe that it's deeply unintuitive that LLMs actually have a particular style that is very discernible. And then I'm going to go talk about some of my work in the area of human detection of generated text, as well as automated detection of generated text. And talk about how these stylistic features have implications with regards to how robust we can make detectors. And then I'll end with a discussion of potential future work. Okay, cool. Oh, I have my water here. Great. All right. So what do we know about the style of large language models? So I'll start with the same feature I talked about earlier. Like I mentioned before, words like delve, intricate, underscore appear much more frequently in LLM text. In fact, recent work that was put on arXiv in late December cataloged a list of these words. And the statistic that I mentioned earlier with delve being 6,000% more likely in an arXiv abstract of 2024 versus 2020 comes from this paper. But it's not just the word delve, although that is the worst offender. There's plenty of other LLM-specific vocabulary that's been appearing more frequently these days. And in fact, it's not just any one particular part of speech. There's LLM-specific vocabulary in all sorts of parts of speech. There's LLM verbs, adjectives, adverbs, nouns, so on and so forth. This is a list that was compiled by a set of expert human annotators. We'll talk about them later on in the talk, but delve features here as well as some of the other words on the previous list. So the reasons for why such LLM vocabulary is so prevalent are not really that well understood. This is partially because big tech companies are loath to release details about the training data of their language models. This may or may not be related to copyright infringement reasons, but you didn't hear me say that. But yeah, so there's plenty of hypotheses maybe related to training data choices, or possibly some overrepresentation in the dialogues that the models are fine-tuned on to become chat models. All of this culminates in humans generally using more diverse language. So with LLMs picking particular words way more often than chance, this seems like a pretty obvious conclusion. Humans have been shown to have a lower type-to-token ratio, as well as higher measures of lexical diversity. And this is specifically on news articles. Okay, so moving one step up from there, we'll start looking at syntactic features. So the next few slides are going to have a lot of numbers, and it's not quite clear what some of these trends are, I don't think they're very well understood. I'm just documenting them. I'd actually really like to get input on people's interpretations of some of these findings, because this is not necessarily my area of expertise. But in general, it seems as though LLMs use more numbers, symbols, and auxiliary verbs than human text, as well as more pronouns, while humans tend to use nouns, adjectives, and punctuation more often. Another important point is that the differences between humans are much larger than between LLMs. On this chart, we have the percentage of all tokens of a certain part of speech across all generated news articles and human written news articles. The H represents humans, and then the rest of all of the columns are the different language models tested. Oh, that's right. Or no, LLMs use more pronouns than humans do. Yeah. Yeah. Mm-hmm. And intuitively to me, this seems reasonable, because pronouns tend to be able to slot directly into the into the as in when you generate a next word, generating a pronoun is typically easier. You don't have to look up any sort of dependency. Um, in the next slide, we have uh, noun phrases, adjective phrases, and prepositional phrases seem to be more common in human text, as well as for LLMs, it seems to be that verb phrases and subordinate clauses are more common. Again, I don't have a good interpretation for this, and the paper that I'm citing is relatively new. And so I think that there's definitely more work to be done, and I would be definitely interested in hearing if there's interpretations of these results. Again, the domain is news articles, and this is the percentage of spans generated by humans and LLMs. Okay. One thing as well that I saw was that it seems to be the case that humans use shorter constituents and exhibit more optimal dependency length minimization. So dependency length minimization is hypothesized to be a linguistic universal and has been seen in many different languages. And that's that the dependencies of your speech or writing, when they're shorter, it's hypothesized that there's less cognitive load on the person you're speaking to or the person that's reading your text. And using this omega score, we can actually measure the optimality of the dependencies. So sentences are compared against the optimal tree structure, and omega of 1 means optimal, and omega of 0 is what you would see from a random sequence. And we can see here the normalized distribution of omega values across the same news articles. And we see that humans are shifted more towards the right, so they're consistently more optimal, and the language models, again, are very consistent. So it seems as though language models write sentences that, not that they're more complicated necessarily, but that they're structured in a way that's less optimal than humans. As a possible confounding factor, the lengths of sentences for language models are much more consistent than humans. Humans write both shorter sentences and longer sentences than LLMs. And as another point that surprised me personally, that LLMs are extremely consistent with their sentence length distribution. And this might continue to affect all of the other results that I've mentioned down the line. So the dependency length minimization, as well as the prevalence of certain parts of speech. Okay. On that note, LLMs tend to make frequent use of syntactic templates. This is a relatively new result from EMNLP. Syntactic template being defined here by one of the 100 most common sequences of part of speech tags of length n equals 6 in the training corpus. So the way that the authors did this is they took the entire training corpus of an LLM, and then they converted all of the words to their part of speech equivalents. And then they looked for the specific 6 grams that were the most common among the training corpus, and then labeled those as templates. And then they quantified how many of the generations from the language model contained at least one of the templates. And across the 8 models they tested, 96% of their generations contained at least one template, whereas for the humans, this was 29%. And this, to some extent, relates to what I was talking about earlier with the generated essays. Like, it seems to be the case that language models use very similar sentence structures, similar clauses, and humans have a lot more variety in their sentence structure. In addition, there was another paper at ACL that used specifically RST tree parses to detect generated text, and claimed that humans had much larger variety in that as well. Sure. Yeah, that's a good point. So I think that in these papers, they're talking about variance across different language models. So we have GPT-4 versus Claude versus Gemini or what have you. I think it is important which language models you are comparing across for this. So, for example, in the previous work, the large language models here, if I had to be nitpicky about their work, all of these language models are very similar to each other. So this is Mistral 7B, Falcon 7B, and Llama 7B. I know for sure that Mistral and Falcon are based off of Llama's architecture and generally share a lot of the training parameters. So they are very similar. This work, I actually forget off the top of my head which models they're using. I mean, Olmo and Mistral are somewhat similar. So it's a fair critique to say that like potentially language models that are much more different could exhibit similar variability to humans. My intuition is that that's not true, but you could look into that for sure. No, not at all. Please. Sure. Yeah, that's a good question. I don't know if necessarily. Um, I guess I guess if we're taking human news articles from, let's say, like CNN or the New York Times, then we are sampling only professional writers, and that it would be a fair question to see whether or not you sample the average high schooler, whether that they exhibit similar suboptimal dependency length minimization as language models. I do think it's nonetheless interesting that language models aren't yet quite at expert writer level. But yeah, that's fair. Yeah, that's true. So not only is it written by human, but there's also many passes done by different people, and so that might explain away the. Right, definitely, definitely. Right, right. You'd have to get people down and write it on a piece of paper and then OCR it. Yeah, I do think that still it is the case that language models can't quite get to this expert writer level. I think that that's fair to say. There's also other works, one that I didn't mention here, that also shows that articles from the New Yorker are vastly preferred to articles written by any one of the language models. So yeah, that's also a really important point. Just to echo that, like the decoding strategy used to sample from the language model drastically affects the amount of variance you see in the output. Um, from what I've read, the overall syntactic structure isn't as affected by temperature because it seems like language models tend to sample from within the same part of speech of the same syntactic template. But that is another good point. Yeah. Okay. Cool. I'll try to make sure I don't keep you guys here forever, so I'm going to keep going. But thanks for the questions. Um, moving one layer of abstraction further out. So it seems as though LLM generated text generally has a bias towards a neutral or positive tone and has little emotional variance. And human text exhibits emotions such as fear, disgust, or anger more often. In the case of news articles, this is probably not intuitive. In the case of a chatbot conversation, this is extremely intuitive to me. I definitely wouldn't want to log on to ChatGPT and then have it express disgust and fear that I would ever ask any question to it, right? But in news articles, again, this is the percentage of articles labeled with the specific emotions, and the humans have more of the negative emotions. Furthermore, LM generated text also is significantly higher in agreeableness than human text. This is also another feature that would be very desirable in a chatbot. You want your chatbot to say, sure thing, I would happily go do this, and not instead disagree with you and say, how dare you ask me this? But not only that, there are actually statistically significant differences in all of the big five personality traits, but they vary in degree of significance across domains, whereas this agreeable one is by far the most consistent across domains. Okay. So to summarize, what we know about the style of LLMs at the current moment is that they use these idiosyncratic vocabulary choices, delve being the most obvious one. They have very low lexical diversity, and they have somewhat repetitive syntactic structures. Their sentences tend to be roughly 5 to 40 words long, and they have slightly suboptimal dependency minimization, as well as a neutral or positive tone and agreeable personality. So, any final questions before moving on? This is my general overview, lightning round of what we know about LLM stylistic characteristics. Okay. So I would like to take this moment to reflect on why I believe it's actually very unintuitive that LLMs have a specific style to begin with. And I think I'm going to try to explain why I believe this, going back to the basics. So LLMs work by taking in a prompt to a neural language model and having them output a distribution over tokens, and then sampling from this distribution to generate the next output token. This sampling can be done, like Mark was saying, with low or high temperature, which means either we pick the most likely word or we sample normally multinomial sampling from the rest of the words in proportion to their probability. And therefore, we generate text by repeatedly sampling this next word over and over and over again. And so during training, our goal is to maximize the probability of these tokens. More specifically, we want to minimize the KL divergence between our output distribution and the one hot distribution of the next word. So if we're going through a training sequence, I'm trying to maximize the probability of yesterday given nothing, and then 4 given yesterday, and so on and so forth. Pasta at home. And I would argue that given this, it should be extremely advantageous for a language model to be able to adapt their style, that is, their relative probabilities given to the next word, to suit the context of what came before it. For example, if in training I see a sequence like this, this is lifted from Shakespeare's Hamlet, as a language model, if I'm trying to predict the next word here, I should immediately recognize, or at least it would be very beneficial to my overall loss, to recognize that this is in fact Shakespearean English, and to adjust my vocabulary token likelihoods accordingly. And we can see that if we run language models with this prompt, they tend to generate vaguely Shakespearean English. For example, this is the continuation I got from GPT-J, roughly similar size model, and it outputs that I do remember an ere a day where we came last foot. Do you so? Well, my dear lord, I've forgotten it, but it was such an ere as did then hang about me, never to be forgot, which I think is vaguely Shakespearean, right? And I double checked, and this isn't just a regurgitation of the exact continuation of Hamlet. This is in fact new text. So with this in mind, LLMs are to some extent modeling the style of what came before and then modifying their own stylistic output to match that. So why then do we see such a specific LLM generated style if they can inhabit arbitrary styles at will as from their training? One more thing to note is that LLMs are actually extremely good at style transfer. So if you've ever written anything with an LLM and then asked it to change it in some way and it successfully did so, you're probably well aware of this. But LLMs are extremely good at making stylistic changes to output text. For example, you can ask it to make text more descriptive, include a metaphor, more comedic, more melodramatic. And so all of these are transformations that the language model understands and can do quite well. So it obviously has a representation of style. And so I would argue that the reason why LLMs show such a specific stylistic tendencies is because of the way that continuation models are trained to become chatbots. So just as a quick overview, the way that we train large language models to become chatbots, this ChatGPT, is that we take the model after it's done pre-training, and we ask it for a set of responses to input queries. So maybe I say, explain to me astrophysics, like I'm 5 years old, something like that. And then it generates a set of responses, and we give these responses to human annotators and have them rank it by preference. And this preference is informed by a set of guidelines that these annotators come up with themselves or are at least given to from on high. So in the case of OpenAI, they spend a lot of time in the paper that first introduces this process, discussing exactly their method for determining this consensus among annotators as to what has the highest preference among the responses. So these annotators rank the responses. These ranked responses are then used to train a machine learning model that is a sort of pseudo-annotator that learns the preferences of the annotator and can then automatically annotate arbitrarily many responses. And then this reward model is used to train a policy model, which is to say, how do I change the large language model's output probabilities so as to maximize the reward I get from the reward model? The large language model is then updated with this policy model, and the process continues. Outputs more responses, they get re-ranked, train a reward model, and so on and so forth. The process I'm describing is the proximal policy optimization algorithm, and this is one of the key algorithms for reinforcement learning with human feedback. And so I would argue that, that the stylistic preferences of the model are informed, of course, by the stylistic preferences of the annotators. This naturally leads us to get these biases. So slight formality, slight positivity bias, slightly longer responses that might be more informative, and a reduction in diversity. This last one I think is really important. Not only is it well corroborated from the literature, it does in fact reduce diversity, but I think that as someone who regularly uses a chatbot service, you definitely wouldn't want the chatbot to suddenly take on a new persona or to suddenly change up its stylistic content over the course of multiple usages or multiple days. Sure.
Arguments in documentation that the preferences for ethnic cuisine types indicate where the annotator included from.
Yeah, I mean, it's a perfect example of how preferences of annotators, even despite all of the efforts from companies to sort of hone them in, they still get baked into this process very, very easily. Right. And so, yeah, so I think that it's important to think about the style of LLMs with a lens to this in particular, as in thinking about, in particular, the difference between chat fine-tuned LLMs that have gone through this RLHF process and have a specific style baked in by the annotators, and then on the flip side, pure continuation models, which might happen to have a style just because they haven't been prompted with anything in the previous context, but might not inherently stick to a style if prompted correctly. This is also reflected in the ease with which you can detect text from these models. So I'm previewing slightly some of the stuff I'll be talking about a little later, but averaged across many different detectors, chat fine-tuned models are much easier to detect than their base counterparts. So in this case, we have the original continuation models from Llama, Mistral, MPT, Cohere, and then their chat fine-tuned counterparts. Okay. So again, I want to remind us of the quote from our journalist friend here, where he was very surprised at dealing with a pre-release version of the Bing chat engine that behaved like a moody, manic depressive teenager and tried to convince him to leave his wife. This is exactly what the annotators try to remove. This is very unintuitive to humans. It's not intuitive that, at the one moment you're a nice, calm search engine, perfect, helpful librarian, and then suddenly you switch gears and you're this this manic depressive teenager. Language models can do that, but we've decided to make them not do that. Okay. So a quick summary, the style of an LLM, in my view, really shouldn't exist if the models are trained purely to predict the next word, or at the very least should get less distinctive with model size. But the RLHF fine-tuning used to adapt models is what gives them their highly distinctive behavior. And this distinguishability will likely remain for as long as we decide it should remain, regardless of how large the chatbots get. So I had a lot of people say that, oh, once we get to GPT-5 or GPT-6, then it'll be truly undetectable even to automatic detection models. And that just is probably never going to be the case. Okay.
putting these chatbots together will or perhaps already have decided that actually, one of them should be like an angry argument or
Yeah, I think character AI is trying very hard to do that exactly right now, for sure. Yeah, so I'm sure that we'll get this this one day. But I think that I think that in general, people want their chatbots to have a personality, not a ball of all personalities at all times. Because that's very unintuitive to people. Okay, cool. Um, So from this point forward, I'll be talking more about the work that I've specifically done over the course of my PhD and relating the stylistic preferences back to robust AI detection. So in particular, I'll be talking about these two papers from AAAI and EMNLP. And these two papers deal with a platform that we built to help test humans' ability to detect generated text in the pre-ChatGPT era, and also to educate them on how to detect generated text in a gamified way. So when we were first attempting to build this sort of platform, we wanted to know how well humans could detect generated text, but we felt like the traditional formulation of the task as, is this text written by a human? Yes, no, had some issues. Namely, first, that we don't learn why the user picked yes or no, so it's hard to interrogate what their decision-making process is. Also, that the setting is somewhat unrealistic. It's usually not the case that everything is all AI generated or all human. It's usually a mix of the two. In addition, our annotators would get tired or bored reading large documents that are all AI, and there was no interactive feedback. So this wasn't really good for gamification, and it also wasn't very good with retaining attention. So our goal was, like I mentioned, to gamify the detection task. And the way we did this is by creating a website. This is roft.io, so real or fake text. This is live right now if you want to go to it. But in essence, it's a platform where you can make an account if you want. You don't have to. And then you can select a domain. So we have news articles, presidential speeches, recipes, and so on. And your goal as the annotator is to decide at what point the text shifts from being human written to machine generated. So at some point, we cut off the text, and then we ask the model to continue the text from there. So for example, I would select it's all human written, and then I would get given another sentence. And I select it's all human written again, and I get another sentence. And then once I think that the text has swapped from being human written to machine generated, I would select this, and I would input my reasoning. And if I got the boundary exactly correct, then I get 5 points. And if I do not, then I get 4, 3, 2, 1, proportional to how close I was to the boundary. Right. So this actually was very effective because we were able to not only get reasonings for why people made the detection decisions that they did, but also the specific sentence that led to their detection decision. And the data from this project is publicly available if anyone wants to analyze it. There's been a few works that have analyzed it since then. Like I mentioned, we have many different genres of text, and the generations primarily come from GPT-2 and 3. Again, this was a pre-ChatGPT era, so unfortunately, we don't have results for ChatGPT in this paper, but luckily someone else has done this work, and I'll talk about their work right after this. Importantly, the study population was 241 students from my advisor's artificial intelligence course. That's Chris Callis and Birch. And when I discussed the results that we found from our experiments, keep in mind that this is not at all reflective of the global population. Again, these are not professional writers, they're computer scientists. Okay. So from September 20th to October 15th, we collected over 20,000 annotations. This actually makes us the largest human detection study ever done, still to this day, actually, surprisingly enough. And our main findings were, the original question we wanted to know was whether or not humans could detect generated text. At the time, this was an interesting question. Right now, it's been sort of beat to death, but our players were not very good. They were better than random chance, and this is on GPT-2, so that's still pretty bad. But if we take a closer look at our individual players, then we'll see something a bit more interesting. So the ability of the players varies quite substantially. So we have a large clump of players that get roughly a score of 1 or 2, which means they're about 3 or 4 sentences away. But there's quite a long tail. In addition, the standard deviation of players, so this is the long tail I mentioned, the standard deviation of players also has a similarly long tail in the opposite direction. So this is the variance across multiple runs of what your score is. And it turns out that the players in these tails are in fact the same players. So our best players had the lowest variance. And if we come back to this chart and we add another column for our best annotator, it tells a very different story, which is that they were able to perfectly guess the exact sentence where the text swapped 70% of the time, 77%, and got the correct side of the boundary 90% of the time. And 77% accuracy, and this is from all annotators who did at least 50 annotations. So it wasn't like they got one or two lucky annotations and then that's it. And this is especially impressive because you don't see further than the sentence that you're on. So you would have to use any feature that's within the one sentence. So 77% accuracy is us being a bit mean to this annotator, and the correct side of boundary is probably a more reasonable definition of a correct guess. In any case, the good players also, oh sure, yeah. Yeah, that's up, that's coming up. The good players also tend to agree with each other much more often. So of all players, they had a Carpenter's alpha of 0.25, but the top 10% of players had a higher agreement. Still not great agreement, but nonetheless higher than the average. So this made us ask the question of whether or not we could train players to perform better over time. And so we split our study group into a control group and a intervention group. The control group received just a fixed amount of extra credit and no help from us at all for completing the task. So they weren't given extra points for doing better on the task or worse. But the people in the study group were given points proportional to how well they did on the task, and were also given a guide document and extra tips from us on how to detect generated text. And it turns out, or sorry, we wrote this guide document. It includes some tips. This was, again, before a lot of the stylistic characteristics were well understood. Nowadays, if we rewrote this guide document, I imagine we would see a larger effect. But generally, we just talked about that ungrammatical text is not indicative of language models, that text that's extremely repetitive is usually indicative of large language models, so on and so forth. It's not that important, the specifics, plus it's somewhat outdated with the modern chatbots. They don't tend to make irrelevant text these days. We gave a quick example of when a language model forgot what the score was in a football game, and we said that this is a very good feature to use. Anyway, okay. So this was the plot that you were asking for earlier on detection rate over time. So at the x-axis, it's how many rounds the annotator did from their 0th round to their 100th round. And our original control group that didn't have any incentives or any tips did roughly the same, if not worse, over time, potentially because they got tired. And with incentives, they did better over time by around half a point. So roughly their score was half a point better by the time of their 100th annotation. Sure. Mm-hmm. Yeah, this is a question that I really should have. If I was a better researcher at the time, I should have split those two groups. But yeah, I have. My intuition is that the incentives probably did more. I'd like to not toot my own horn. Yeah.
Even though you've done your best to gamify it, it's still not that exciting a task.
Right, yeah. It is quite hard if you want to try it on your own. I'm also not that good at it myself, to be honest. So, but yes, so we wanted to check out what specifically our players were learning, or if there were any difference in what features they selected for their rationales between the good and the bad players. And in our error taxonomy, I want to focus on just these two specific errors. So the grammaticality one is, I would say, somewhat of a red herring we put there. We know that this is not a very good reason, but we put it there anyway because some people use it. And red herring is the wrong word, but you know what I mean. We put this there hoping that people would select it. And in fact, the mean score of players who, for all annotations for which a player selected grammatical error as the error, the mean score was the lowest among all of the rationales. And common sense, irrelevant sentence, contradicts itself, were consistently the highest. And again, like these features are at a very high level because we didn't necessarily understand what we were looking for at the time. We sort of had to guess, what's our taxonomy of language model errors? Nowadays, if I were to redo this study, I would probably go much deeper and do a more sort of linguistically minded selection of errors. Right. In addition, the identified errors changed a lot across different genres of text. So the yellow pie slice represents common sense errors, and they were much more common, we found, in recipes than in the other two domains. Likewise, the gray pie slice represents generic or uninteresting text, and this seems to be much more common in news-like text than it is in recipes or short stories. Cool. But the question on people's minds is probably something like, does this also apply to LLMs post-ChatGPT era? And thankfully, as of literally 2 weeks ago, sorry for the very small text on my slides, but this says 26th of January, 2025. So roughly 2 weeks ago, someone from University of Maryland redid our study, but with ChatGPT, and they found some really interesting things. So I'll quickly recap what they found. So the first thing is, and again, sorry for the small text. The first thing is they had populations of non-experts and experts. So they asked people how often they used large language models, and the expert population was either weekly or daily, and the non-expert population was few times or never. I'm noticing now that there is one non-expert that is daily. Potentially, these are preprint problems. But in the passage, they mentioned that daily or weekly, you're an expert, and then less than that, you are not. Okay. There is more detail on the pilot study. They recruited their annotators from Prolific, and they gave them guidelines on how to detect generated text. And they were able to find that the non-experts detected text at roughly what we would expect from the Turing test results I mentioned, so 56% on average. And then the experts detected text at a rate that is much, much higher. And interestingly, they had similar confidence levels. These were the reasons that their annotators gave for their decisions. So at the top was this use of LLM vocabulary. So roughly 53% of all rationales from the annotators' decisions among the experts were due to LLM-specific vocabulary. And the next most common was the sentence structure. So the syntactic features that we mentioned, short, choppy sentences and paragraphs were indicative of humans, and indicative of AI is it's not just this, it's this. Right, or listings of specifically 3 ideas, which is something I immediately noticed as well in the LLM generated essays. Likewise, grammar and punctuation, AI models do that perfectly. Humans don't tend to. And then, the list goes on. I highly recommend reading the paper if you're interested. This work is really, really, really well done, and I'm lucky that they put it out right before I was set to give this talk. So one thing that they asked in this paper that I found was really interesting as well is what if we specifically took the features that humans used to detect generated text and then prompted the LLM to not use them in generation? Like, is there any way to ask the LLM not to use its intended original style? So they wrote this big prompt template. It starts off by saying you are a journalist writing an article for so-and-so, and then lists their entire AI detection guide, which they compiled over talking with all of their experts as to what features, the list of vocabulary, so on and so forth. Then they give examples of human and AI written articles, and then ask them to follow the specific guidelines to make your article seem like a human wrote it, such as follow the detection guidelines, do not use any of the overused AI words or phrases, metaphors, grammar patterns, so on and so forth. And so in essence, what they're trying to do is they're trying to humanize the text, which is typically what the term that we've decided to call this, which is trying to get ChatGPT to sound less like ChatGPT and more human. But amazingly, prompting was not able to remove the LLM style at all, even with all of the specific guidelines. So the specific column here is this O1 Pro humanized. So that's a GPT-4 O1, the most recent model, with this humanized prompt. And while certain annotators did get tripped up, like it seems annotator number 3 went from roughly 100% accuracy down to 0 on O1 Pro humanized, the majority vote of the annotators was still perfect accuracy for what I believe is, I think it was 300 articles. This is the best result I've ever seen for human detection of generated text. In fact, the majority vote of human annotators outperformed even the state-of-the-art automatic detectors, which is really, really impressive. And I guess it just goes to show how distinctive the AI style is. Yeah, I was very impressed by these results. So, if it is possible for humans to robustly identify generated text, even when we try to prompt away the specific features that we're looking for, does that mean that we can robustly identify generated text automatically? Like, how good are classifiers at doing this? How well do they learn the stylistic tendencies of large language models? So this section, I'll talk about these two papers, the one from ACL and then one that I just got done presenting roughly a month ago, based off of the original work. So to answer the question by just looking at the related work, it actually is very easy to detect generated text. This is purely if I were to look at all of the related work and see what accuracies they're claiming to get on generated text detection. So these are all of the state-of-the-art results, and all of them seem to claim 99%. For example, the last one, Winston, this is a commercial detection company, and they claim 99.98%, which is just incredible, truly. The problem is that in reality, we see these types of stories about AI-generated text being impossible, and that OpenAI is pulling their AI detector due to low accuracy, and that students are getting incorrectly flagged as AI and then failing their class, and so on and so forth. So it seems as though the boots on the ground reality of detection and the reality in the academic world are sort of at odds with one another. So what's really going on? So we set out to build a large-scale benchmark for AI detection. We just tried to make this benchmark as large and as difficult as we possibly could. So we got over 10 million generations from 12 large language models across 11 domains with multiple decoding strategies, penalties, and then applied adversarial attacks to all of them. And then on our data set, we benchmark the performance of the supposed state-of-the-art detectors and see how well they do on cross-domain and cross-model robustness. And then we also put up a leaderboard for people to submit their detectors to see how well they do in comparison to the state-of-the-art, to sort of centralize the evaluation landscape. As a quick overview, these are the models and domains included in RAID. RAID also, as a quick plug, I guess, RAID is also very useful for looking at the differences between different language models given the same identical prompts. And so one of the uses that we haven't seen so far of RAID would be to do this sort of linguistic analysis across different models and domains. So if anyone is really interested in doing that, there's plenty of data for you, and I'm happy to chat about it. But yeah, this is the overview. And I'll talk really quickly about the major findings we found for automatic detectors here. The first thing is about the false positive rate. So false positives being defined as when you incorrectly label a human written piece of text as AI. So false positive rate is a really difficult problem to solve. I don't know if it's fair to phrase it as a problem, but the point is that the false positive rate you operate at depends on what you set your classification threshold to. So if you set your classification threshold very low, then you label everything as a positive and you have 100% false positives. But then as you sweep the threshold up, you have lower false positives, but also higher true positive rate, and so on and so forth. And of course, since false positives in many scenarios cause a lot of harm, in the case of academia, it could cause you to fail your class with an academic integrity violation if there's a zero tolerance policy. Our ideal operating point is probably somewhere around here, which is an issue because when we restrict ourselves to very low false positive rates, we also might restrict ourselves to low true positive rates, which means we have low recall and we can't actually get any of the AI-generated documents. And so we actually graphed the false positive rate versus true positive rate for all of the detectors that we tested on RAID, and we found that despite the claims of the paper authors that the true positive rates of 95% or higher were really only positive, accounting for a 10% false positive rate or higher, which is usually unacceptably high. Furthermore, when going at a a reasonably safe false positive rate of 1%, which is, if you're teaching a class of 500 students, that's 5 incorrect AI classifications per class per essay. So that's being pretty generous at 1%. Models don't get higher than 60% recall, generally speaking. There's one outlier, the binoculars model, and that's gone on to be the current state of the art. It does actually quite well at lower false positive rates, but nonetheless, many detectors struggle, despite what would seem like high accuracy numbers. So another thing that we found is that a lot of detectors have really poor robustness. They actually seem to be very brittle when you change the generative model or change the domain. And this is a chart where, or sorry, I should say a heat map, where we graphed the recall of the detectors at a false positive rate of 5% specifically. And the GPT-2 detector really only does well on GPT-2 and fails on other language models. And likewise, GPT-0, which is a common commercial detector, does really well on ChatGPT and GPT-4, but fails on the open source models like Mistral and GPT-2. So it does seem like the different LLMs, while previous work has talked about how consistent their styles are, it may be the case that automatic detectors are overfitting to particular language models and not picking up on the shared stylistic sort of undercurrent of all of the language models, if there is one. Likewise, there's also detectors that fail in particular domains. So radar had a very acute weakness to movie reviews. So pretty much any movie review is basically a coin toss, and then it did great everywhere else, which is very interesting. So the last thing I wanted to mention is that adversarial attacks are very effective at fooling detectors, but the effectiveness depends on the underlying model used for the detector. So detection is fundamentally an adversarial problem, so it's important to at least appreciate the adversarial nature. For example, if I gave these two texts, the one on the left being the original text and the one on the right being the altered text, can anyone notice what's different about the right text versus the left one? Yeah, the spaces. And you might also be interested to know that this causes roughly a decrease of 14% in the recall of classifiers on average across all of the ones that we tested, some of which had higher drops and some of which had lower drops. And similar very small scale attacks that you wouldn't think would have a large effect on detectors actually had quite a large effect. That would be swapping uppercase, lowercase, deleting articles, swapping synonyms, misspelling words, and then adding in homoglyphs, which are characters that are not, they're characters that look similar to ASCII characters but are different UTF-8 encodings. And across all of these attacks, we can get quite a large drop in recall, sometimes taking classifiers from 70 or 80% recall down to basically 0. So with all of this in mind, you might think that this is us being a little bit unfair because we're using all of these adversarial attacks and domains and models that the classifiers have never seen before. But what happens when you train on RAID? That is to say, what happens when you know all of the adversarial attacks in advance, you know all of the domains and the models, and you have plenty of in-domain data to train? Can we then get the accuracies that we see originally in the claims of 99%? So in order to test this, we actually organized a shared task at Coling 2025. The research questions, I laid them out earlier. Can a single detector learn to recognize the style of many different LLMs across domains accurately? And then also, can a single detector be robust to many different known adversarial attacks? So like I was saying, we organized a shared task to get to the bottom of this. Phase 1 was we released the training data, that is the RAID data set, and some baseline results. Phase 2, we conducted the official evaluation and released a leaderboard. And then phase 3, we had people submit summary papers of the systems that they submitted to the leaderboard. We had 2 subtasks. The first task was the non-adversarial task, and the second one was the adversarial task. We also gave participants access to all of the code used to generate the adversarial attacks, as well as access to the original source domains for the human texts. So we gave them the large-scale data sets from which we sampled our human texts. So The results of the task actually really surprised us. I don't think that I was prepared for how well the detectors actually ended up doing. But we found that on subtask A, our best teams did over 99 TPR. We had multiple teams do over 99. And this is at a false positive rate of 5%, which is admittedly generous, but we didn't really expect people to do this well. And then likewise on the adversarial task, people did over 97% TPR. And this is across 12 different language models across 11 different domains for a single detector. And of course, the previous state of the art from our public leaderboard was much worse than this. Some broad trends for how people got this high accuracy really quickly, sampling hard positives and negatives, namely looking at examples where their detectors did the absolute worst on, and then using them only in the training process to improve the detectors. Similarly, pre-processing and normalizing their input worked very well, especially against homoglyphs and some of the other more annoying adversarial attacks. And then finally, finding extra data to utilize was broadly helpful. One of our teams actually used authorship attribution data. So they had texts from different human authors and then trained a model to represent those authors with embeddings, and then fine-tuned those embeddings on generated text, and that actually worked pretty well. But nonetheless, the takeaways from this shared task is that actually, sorry, hold on. Yeah, well, the takeaways, I'll talk about the takeaways, is that detectors actually do pretty well with in-domain data if they have enough of it. So we can actually automatically recognize the style of large language models, and we seem to be able to recognize the style of arbitrarily many models as long as we have enough data for all of them. And so what this leaves us with is the problem of robust AI detection in new models and new domains as the main area of research for detection. And then furthermore, another area of research is in hybrid human-machine written texts. So how texts change when you output them from an LLM and then further edit them as humans. They may not be detected as AI generated. But there's also a fair point to be made that that might not even considered that might not be considered AI text to begin with. Right? If you edit something enough, is it AI generated? I don't know. Anyway, now where does this leave us? We've established that LLMs do have a unique and discernible style, and that to some extent it's reflective of the specific annotators that were used to train the models. Furthermore, this style can be robustly identified by humans, and it's non-trivial to remove via prompting. So humans, to some extent, are robust to different prompts and to different domains. However, the style is identifiable by automatic detectors, given enough in-domain data, but is very hard to detect when out of domain context and on models they haven't seen before. But there are a lot of questions left to answer. One of the ones that I'm most interested in is whether or not there's aspects of LLM styles that are inherent to the modeling process, or that all aspects of styles are just reflections of the annotator biases that train them through the reinforcement learning. Another thing is whether or not we can see aspects of style within the pre-training corpora. This question is probably going to take a while before it's answered because, again, all of our most capable models don't have public training data. There are a few that do, and I'm looking forward to studies on that. And then finally, is there a world where we can have AI detectors that detect the parts of LLM styles that are shared between different models that therefore could then be robust to models in different contexts and different domains? One potential future area that I think is really cool is interpretable detection. So this is a screenshot from a commercial detection tool called Pangram, where they highlight specific syntactic phrases and other n-grams that are really, really indicative of AI, at least as some sort of an explanation. This is a good step in the right direction, but my dream is to have an AI detector that just takes in a document and then responds by explaining to you that this document is AI written because of the following features, and that these features are significantly more common in LLM generated text, and that you can then make a decision as to whether or not you believe the detector based on its rationale. And in my view, this might be able to reduce some of the false positives in the more critical areas, or at the very least, we can gauge our own ability to trust the detector based on the rationales given and not based off of blind faith. And this to me is very important because bad AI detection does cause real harm. I'm bringing up the same headlines as before, but just to remind everybody that there are many, many cases. If you search for, my professor said I'm cheating, but I'm not, all over the internet. Who knows whether they're telling the truth or not, but at least from what I've looked into, false positives can and do happen all the time. All right, so this is the end of the talk. I hope I didn't drone on for too long. Thanks so much to Annika for inviting me, and happy to take questions. Mhm.
So, like, result, it's hard to just talk the AI into not making certain mistakes. It doesn't really work.
Right.
But if I want to make undetectable text, that's what I want to study.
Right.
Because then that's the argument.
Mhm.
So, do you have any intuition about why it's hard to push them around? Because it does seem possible to push them around in other ways.
Yeah, so this was actually a really unintuitive finding for me personally, which is why I included it. And to be clear, this work wasn't my finding per se, but it's the paper that was published 2 weeks ago. I think that I think there's probably a lot more ability to push these language models around when they aren't as constrained by the reinforcement learning. It may be the case that because they used the O1 Pro model, this model has undergone a ton of reinforcement learning training to do these sort of reasoning traces, the think tokens, and all of that. And that may be constricting the style of the output. This is just a guess on my part, but this seems reasonable to me that the more reinforcement learning you do, the more sort of stuck in a specific style you get. But to your point about the sort of arms race, like I think that in general with detection, I think a reasonable goal is to try to catch people who are lazy about chatbot usage to some extent. Right? If you just say, generate me this, or generate me a news article that says bad things about my political opponent or something, generate, copy, paste, then we should aim to be able to detect that. If you're extremely sophisticated and you fine tune your language model on a specific author from the New York Times and generate text in their style, there's really nothing we can do about it. And especially with the sort of breadth of possible adversarial attacks that you can employ, detection in that sort of setting is really, really difficult. So.
I was wondering that don't really have the right baseline. Right baseline to me seems to be take a whole bunch of paragraphs, have large language model continuations, but also have humans produce those things. See how often people false alarm on humans because another author trying to generate a style similar to what has just been read, right, is going to probably throw some features in there that would cause people to say, oh, it's actually other thing. How much of this is detecting a model versus detecting model change?
Yeah, I think anyone who's attempted to continue a piece of Shakespearean English knows how hard it is to match the style of something that's gone previously. Right, exactly, right. Like I think that in that setting, it would be much more obvious what is human written text and what is LLM text just by the change in authorship being very abrupt. As just my own baseline intuition, I think when LLMs continue text from previously, it's not as abrupt an author change as I think you're suggesting. Like I think that LLMs generally are able to continue text quite well without it seeming like it's sudden change. I think that at the very least, our study worked only on continuation models and no chat models, so they're trained specifically to continue that style. And so I think if I'm answering your question correctly, what you're asking is like, are humans detecting the change in authorship or are they detecting LLMs? I think that they're detecting LLMs in my study. Um, just because I've also done it myself, and I don't think that it's an authorship change as well. Okay, I guess In some ways, if an LLM starts to mess up after continuing text, then that is in some ways an authorship change. So I guess that is a different setting than detecting text that is completely from start to finish LLM. I've never thought about that before. I think
It seems like that would be getting 100% majority response. I strongly suspect that some of that is just people detecting a change, not AI.
yeah. So the Maryland study actually doesn't do continuation at all. Their study is purely like write me a news article and then it's fully AI generated. So for my study, yeah, that's possible. But for their study, they actually are there's no authorship change at all. One more comment on that is that we actually had a baseline where we just stitched two articles together from totally different authors in our study and tried to get an idea of how well humans could detect that as a sort of like baseline easiest possible task, and that was significantly easier than the LLM task. Sure.
In the old days, or the internet existed, was language models, authorship changes were the main way of detecting cheating.
Hmm.
Students have an assignment or a topic, often they would stitch it together from bits of published articles.
Mm-hmm.
Library. Where you would say, wait a minute, that this paragraph doesn't really quite fit with the previous one, either discourse-wise, stylistically, and then we would do a little bit of searching and talking to the student and discover, yes, they had copied it from different articles.
Hmm.
Of course, the other thing that was harder to detect, except in cases where that kind of thing happened, was when they hired somebody to write the
Okay.
student having stitched together paragraphs from several sources, brought them in and confronted them with it, and they said, "God damn it, that guy swore to me that he."
So they hired someone to write something for them, and then that person then it comes full circle. Yeah, it's interesting to think of the differences between detecting the change in authorship and specifically the authorship style of LLM. Yeah. Yeah. Oh. Mm-hmm. Yeah, that's a really interesting point. So in terms of detection work on multilingual text, it's definitely a lot less common than detection work in English, as is the case for a lot of NLP research. There was so as part of the shared task that we participated in, there was another shared task that did detection across many languages, and that was like their whole point of doing the shared task was to sort of broaden the scope. I don't remember many details from the paper in terms of like stylistic attributes in other languages. Also, as a non-native speaker of those languages, it would probably be harder for me to understand. One thing that I think, and this gets back to the point you were saying about the reinforcement learning, is that if we have annotators that are doing the tuning, reinforcement learning tuning in English, then it may be easier to detect the style of the language model in other languages because they might reflect stylistic biases of English writers, or at the very least, if most of the RLHF annotators are coming at the process with preferences for English language chatbots, then potentially either translations or distillations of that process to other languages might be a lot more detectable. So that's my intuition, but I actually don't know, and I'd be right, and they won't tell us anything about them. Yeah. I from what I understand, it's some combination of translation and then some little bit of actual fine tuning. But again, like all of these things are trade secrets, so it's hard to work on this sort of stuff specifically. But yeah, this is a good area for work, sure.
Might also be trade secrets. In psycholinguistics and like sentence processing studies, like something on prolific or NCERT, there was like a string of papers that was like, like annotators don't always, or like the people that you're getting these judgments from, or like your data from, are not always really paying attention or like doing the task very well.
Yeah.
And so like there was kind of a lot of work on how to ensure certain quality with respect to your data, and like if you can kind of translate that to an annotator sense in the, well, what if they're just choosing the longest one because it's most likely to be informative, they don't actually want to really read it. Like those sorts of ideas, and how people like looked into potentially creating metrics that might correspond to biases like that.
I don't think people have looked into that specifically from what I've seen. I do know that at the very least, both myself and the Maryland study put in attention checks for our tasks. So my own attention check was periodically throughout the real or fake text process, you would get a set of sentences that would say, please select me. And if you didn't select those sentences more than 80% of the time, you were excluded from the annotator pool. But I wonder if we went back and looked at the data, we discarded what people were. I guess, are you asking like what are people looking at when they're not paying attention, or is there like a bias for a low attention version of the task?
Not necessarily with respect to like your studies and your participants, but more with respect to like the annotators and their kind of whether or not their biases might be tied to wanting to spend as little cognitive resources on the task as possible to still get paid.
Yeah, do you mean the RLHF annotators?
Yeah.
Sorry, I totally misunderstood. Yeah, I again, all trade secrets. There's genuinely no way that I can know. The paper for RLHF originally that went into a lot of detail about the process detailed a bunch of different methods that they used to check the attention and to make sure everyone was on the same page, and then do regular audits of specific annotators if they moved from the consensus a significant amount, and the ones that had the lowest agreement, they would sit down and talk to them. So they really took it very seriously, and I think that's part of the reason why OpenAI released such a good chatbot so early on, is because of this sort of process. So I imagine there's a lot of work that's being done on sort of erasing the biases from RLHF annotators that are not paying as much attention to the process. But it is interesting to think about what, if any, are the biases that make it through that filter. Like, is the sort of is the sentence length result that we see a factor of potentially annotators just sort of not paying attention, saying, this sentence is long, it seems informative, that's great. I personally think that the longer the responses are, that the really long ChatGPT-like responses that it gives you, very, very detailed, are just overly selected for in the RLHF process. And that's probably just because longer equals better usually. And so that might be part of it for sure. Yeah, no problem. Okay.
How do you classify the reference as a calculus sign?
Yeah, so this is one of the features that I thought could potentially be a LLM universal, because all LLMs have a sort of fixed context window, right? And so for any entities that were last referenced from further than 8,000 tokens ago, LLM has no idea that they've ever existed. There's no long-term memory whatsoever. And so back when LLMs had much shorter context windows of 500 or 256 tokens, I thought that this could be a really interesting project idea to look at the co-referring entities and seeing that human text may have longer co-reference change than LLM text. And there actually was a paper, I don't remember the name of it, but it was somewhat recently that finally did do this study and confirmed it. But I don't think the effect is as large as some of the other features mentioned here. And then also,
Definitely within the number of- I'm thinking about the word, say, they use the terminology like sentiment theory, right? When you talk about something, even when you change it to a new object within the window of, say, 5 sentences,
right, right.
there has to be some natural discourse strategy to shift from one sentence to the other. If you divide them, they're completely grammatical, and they sound really off.
Right, right.
I think those are very easy to apply.
Yeah, I think it would be a really interesting study to do. From personal experience, I think that older models tended to do this sort of rambling on and sort of losing the focus of what they're talking about more often than modern models. I think that might be a factor of, we keep coming back to talking about the reinforcement learning process, but having something that comes to a reasonable end, that is sort of cohesive, that is centered around a certain topic, it seems like modern language models do this fairly well. So I think that the feature is probably less predictive now than it was at a certain point in time. But I would be very interested to see this sort of study. And I think that these sorts of studies are actually really sorely missed in the detection literature. Everyone sort of takes their favorite pre-trained model, fine-tunes it on detection, and then says, I can solve the task. Whereas comparatively fewer people are looking at the specific features and saying, hey, language models fail to do this specific thing. So I would love to see a study like that.